He's currently at NASA Goddard, and his areas focus on assessment and improvement of global reanalysis. And so, as you can see, he knows a lot, and looking forward to your presentation, Richard.
Okay, I'm going to try to keep within time, so I'm going to share screen. Can you see my screen?
Yes, thank you.
Okay, so I was asked to talk about initial conditions for the sea ice outlook. And as an atmospheric scientist, I'm always happy to talk about sea ice to other atmospheric scientists. Let me go to full screen here. Okay, so very quickly, the sea ice outlook, which had its summary as part of the sea ice team yesterday, is a proof of concept forecasting, seasonal forecasting contest that's been going on since 2008. There is a tremendous interest in the sea ice forecast that are generated from this contest. There's particular interest from the modeling community and other communities as well for contributing and seeing how their forecasts do. So the left figure here is of the number of contributors over the years. The right figure is kind of showing how we do. The red line is the observed extent, and the shaded area here is the intermediate quartiles from the forecast. So sometimes the forecasts are right and sometimes they're wrong. So the rationale for sea ice predictability is that Arctic sea ice has a decorrelation timescale on a seasonal timescale. So there is quite a bit of evidence that seasonal forecasting could be conducted. There have been some studies which show that you could forecast for longer periods of time. But the experiments have shown that there's an importance in initial conditions, and in particular, the sea ice thickness is important for predictability. So the bottom figure here shows a study by Ed Blanchard-Wrigglesworth, which surveyed a lot of the people, the models that participate in the sea ice outlook, and they gave them a standard set of initial conditions to see how they forecast. So the bottom figure here shows the sea ice extents. They're all varied from these forecasts. They're all varied because each of the models has a different land ice boundary to them. Once that's normalized and you look at the anomaly, they all tend to agree fairly well. The gray line here is the observations then, and you can see that they all tend to do reasonably well if they're given a good set of initial conditions. So this year there were 15 dynamical model predictions, and that included 10 global atmospheric and ocean model predictions. And most of these came from the North American multi-model experiment, which is I'll talk about a little bit here, which is that's a system set up by NOAA essentially to forecast El Nino with global forecasts. And it's based on a large suite of hindcasts going back to 1981 to normalize these forecasts. So, and remove the model drift. So there's a large library of hindcasts that are produced to make these forecasts. Most of the initial condition data assimilation is fairly simple. There's an ocean data assimilation system that's performed separately from the atmospheric data assimilation, which is usually borrowed from some operational or analysis or reanalysis. Nearly all the systems do not incorporate observed sea ice thickness. In fact, many of them use the reanalysis surface temperature as a constraint on their sea ice, so they don't even incorporate observed sea ice concentration. And the differences among the models can be large. So this is briefly discussing the multi-model, North American multi-model ensemble. So again, many of the models that participate in this serendipitously grabbed the sea ice from these forecasts and submitted them to the Sea Ice Outlook for a seasonal forecast of the sea ice. So this is kind of my important slide here. This shows what data sets are being incorporated into the Sea Ice Outlook for initial conditions. And so you can see for a seasonal forecast, the initial atmospheric condition is perhaps not that important. The ocean observations, which I'll talk about a little bit more in a moment, there are various methods for incorporating those into an ocean analysis. In terms of sea ice concentration, many of them use several of them use the passive microwave, but many of them, as I said, just constrain their models based on the 2-meter temperature from the reanalysis, the atmospheric forcing data that they're using. And most of them do not incorporate any observed sea ice thickness. Biomass is a regional, ice ocean regional climate model. It doesn't incorporate observed sea ice thicknesses. This year, the GMAO submitted an experimental forecast where we tried to insert observed sea ice thickness values. And again, from the theoretical evidence, it suggests that sea ice thickness is kind of the key for producing seasonal forecasts. So the ice and ocean components of the models, the ocean reanalysis, have been evaluated as part of the Ocean Reanalysis Intercomparison project. That's an international project to evaluate ocean reanalyses. And the results are kind of sobering. So this is an example of the mean ice thickness from several ocean reanalyses for the month of March. And they're all, they spread the gamut. They're all over the place. As you can see, in terms of the sea ice volume then that's derived from these ocean reanalyses, then they have extremely varied initial conditions. So this uncertainty in the initial conditions contributes then to the uncertainty in the seasonal forecast that's produced. So this is these are the results of the sea ice outlook for 2 particular years, 2015 and this past year. And I've used a red dashed line here to indicate what the actual observed values are. So the green lines here, the green bars indicated here are dynamical models. And so as you can see in 2015, they were kind of spread around what the actual value was that was realized. So this is a seasonal forecast beginning in early July that was submitted to the Sea Ice Outlook in early July of the mean seasonal sea ice extent for the month of September. Here on the right is for July. And as you can see, a lot of the green dynamical models underestimated what the forecast was. Again, there's no observations going into the initial conditions. We had a very warm winter. We had record low sea ice for January, February, and March, but the sea ice seemed to recover in the spring. The amount of data that's going into these seasonal forecasts, though, is limited. As I showed, there's no sea ice thickness going into these observations. And so it seemed like a perfect situation where the forecasts were confused based on those initial conditions. And so they're kind of caught out. So quickly, some potential sources of Arctic data that are available for improvement for ocean reanalyses. So there are several centers now that are producing sea ice thickness data sets that could be used. And they're derived from either the SMOS satellite or from the Cryosat-2 radar altimetry. ISAT-2 is also to be launched in 2018. And so there's perhaps an opening coming up here for improved sea ice thickness to go into these forecasts. In terms of ocean data sets that go into the ocean reanalysis, there are these Argo profiling floats that are globally distributed. They have extremely limited coverage in high latitudes. You also have buoy data from the International Arctic Buoy Program. Those make their way into the atmospheric reanalyses in one way or another. They are distributed on the GTS. Underneath the sea ice, there isn't that much data. There are these ocean ice tethered profilers, though, that have been put into the Arctic since 2005 or so, and those are provided by Woods Hole, and so they do provide continuous ocean temperature and salinity profiling. But they have limited coverage and they're not available on the GTS. So going back to sea ice thickness, or sea ice data, there are some difficulties in using or assimilating those data sets. They have limited spatial coverage. Their timescales are kind of the issue here. So in an atmospheric reanalysis, you have a window of 6 or 12 hours for observations to make their way into the data sets. For the Argo floats, which are used for ocean reanalyses, they tend to have a 10-day repeat cycle. So again, you have this mismatch then in the windowing then between the ocean and the atmosphere. There are some difficulties in characterizing the spatial uncertainty for the sea ice thickness. So ice thickness is based on the difference between the open ocean areas of observed altimetry and the freeboard that's obtained from the radar altimetry within the ice pack. And so the distance then between the open water and the ice pack can lead to additional uncertainties then. And then you have to translate that data into the model representation of sea ice. Sea ice has various models, generally have sea ice categories, which are used for describing the sea ice in the model. And so there's kind of a black magic then to take the observed altimetry value of sea ice thickness and convert that into one or several of the categories of sea ice thickness that's in the model. There's also the problem, of course, of snow on top of the sea ice as well. And then finally here, I wanted to talk about prospects for coupled atmosphere and ocean reanalyses. So one of the problems in atmospheric reanalyses, of course, is that they have very simplistic representations of sea ice. And so they have issues with the surface fluxes in the atmosphere. They usually assume some type of uniform sea ice thickness, or in the example of MERA 2, they have an even simpler representation of sea ice where there's just a relaxation time that's imposed. So trying to get better surface fluxes suggests a more complete model representation of the sea ice. And as part of that, you might want to go to coupled reanalyses. The drawbacks, again, are the mismatches in the timescales. You could also, between the atmosphere and the ocean, the deficiencies of those individual models may be amplified when they become coupled. So there's a spectrum of interaction that's associated with coupled reanalyses. In one sense, you could have a strongly coupled reanalysis where you have a minimization of a joint cost function that controls both the atmosphere and the ocean and perhaps the sea ice as well. That's very complicated. I'm not aware of any center that's going directly to try to address that. You have, on the other end of the spectrum, quasi-weakly coupled assimilation, which is essentially what's being used now to initialize these models. It's some type of atmospheric reanalysis then, and then you try to come up with something in the ocean. And then you have everything in between, such as a weakly coupled analysis, such as I believe was used for the CFSR, where you had an individual model, but you had separate data assimilation occurring in the atmosphere and the ocean. So those were the comments that I wanted to make with regards to the initial conditions that are used for the sea ice outlook. Are there any questions? We have 3 minutes remaining.
Richard, Andrew Roberts speaking. I'd like to know if you have ever thought of assimilating sea ice freeboard instead of thickness, because that's what's directly observed by ICESat and will be by ICESat too.
Yes, I don't have any particular knowledge. Well, I know there are people in this bill at NASA who are looking at assimilation of sea ice properties, as opposed to what we did in our experiment for this past year, which was simply to insert initial conditions and essentially nudge the model towards those initial conditions. I believe, I guess, as I said, there is still the uncertainty associated with perhaps snow on top of the ice as well, and so those are additional issues associated with assimilating the freeboard. That's about all I know with regards to that.
Okay, thanks.
Any further questions? Richard, being one of those atmospheric folks that are largely ignorant of sea ice, I really appreciate your talk. I learned a lot.
Thanks. I'm a bit ignorant as well. I had a lot of help from the people here at the GMAO. So, yeah.
As usual, I was trying to unmute. Sorry. I had a question. You kind of showed the NNME plots, but none of them, and you kind of indicated that they participated in the CI's forecast. How did they fare? Were they among the slides that you showed? Were there results?
So they are on the, in this figure on the right here, I've starred the coupled atmospheric ocean models. So I believe the UK Met Office participates in the International Multi-Model Ensemble, but certainly the GFDL model does. The NCEP model does. I believe that's the CPC version of the model. Chingren might correct me on that, but I believe that's the CPC version of the model that contributes to the NMME. And then, of course, there's us, the GMAO. My conjecture is that, you know, for the multi-model ensemble, you require a huge number of hindcasts. We have one of the smaller ensembles for our seasonal forecasting. So there's around 7,000 hindcasts of 9-month model integrations that have to be produced. So you won't see year-to-year improvements from these models. That's just because of the enormity of reintegrating all of those hindcasts. I believe a lot of the movement in these forecasts is in the statistical methods, which seem to be greatly refined from over the years. So at some point, there will be some improvement in the coupled models when additional information goes into the initial conditions. But that might be, you know, until they reintegrate all of their forecasts. For right now, you can see that the statistical methods appear to outperform the dynamical models for this past year. And so my conjecture is that that's going to be the way things are.